We are starting our one of many subtopics or sub-scientific principles that we're going to explore in order to piece together how to understand sea level rise and if that really is a risk that we should be concerned about. And as a result, how to interpret any data that we get from, I don't know, experiments taken. I don't even know how they actually do these labs. I think it's really cool, but I don't know how they do them. But anyway, our first kind of subtopic that we're addressing and to understand the full picture of global warming within the context of sea level rise is greenhouse gases. So you guys did a PhET simulation, and what you should have found is as far as energy light spectrum, you should have found that the higher energy pairs were ultraviolet, gamma, X-ray, and visible. Most of you should know what the electromagnetic spectrum is. I think it was discussed in 7th or 8th grade, and then definitely if you took physics. It's just a representation of the relative energies and wavelengths and frequencies of all possible waves that exist out there in the universe. The higher the energy, okay, they're more associated with like radioactive waves, right? High energy radioactive waves. But the shorter the wavelength and the higher the frequency. Each subcategory of wave, each region of wavelength, okay, each region of wavelength, because the wavelength works like this. You have a spectrum, and you say that within a range, you might call that UV, or within a range, you might call that visible. Waves displaying this particular range of wavelength have various characteristics that are unique to that category. What we're going to find, and hopefully that you guys found, is that a distinctive wavelength is critical in identifying whether a greenhouse gas or whether gas is a greenhouse gas. Okay. So you guys maybe made a prediction, maybe you didn't, but then you did your little that simulation kind of moving of the particles. And it's really kind of funny because particles actually stretch, twist, bend, and twerk. Particles, when shot with a certain amount of energy, the bonds actually move. And it's really cool. And we actually use a specific analytical instrument known as infrared spectroscopy, where we shoot rays. And from that, we can determine the structure of a molecule depending on how it moves, given a certain wavelength shot at it. So it's actually a very high level concept that's applied in higher levels of chemistry that you're just seeing at a very fun level with the simulation. Okay. But what did we see about carbon monoxide? Which did it move or respond to? Which region of wavelengths did it move or respond to? Evelyn? Excellent. Microwave and infrared. And then nitrogen and oxygen, did it respond to any of them? No. Okay, what about carbon dioxide? What did it respond to? Infrared. What about methane, CH4, carbon tetrahydride? What did it move to? Infrared. What about water? What did it move to? Microwave and infrared. What about nitrogen dioxide? All of them. And then what about ozone, O3? Excellent. So what you get is this kind of spectrum of, or this data table showing response to various waves for from a given molecule. And what did we see? Which molecules were not affected by the radiation in the simulator at all? Well, that would be N2, diatomic nitrogen, and diatomic oxygen. But what we did see was that for carbon monoxide, carbon dioxide, methane, water, nitrogen dioxide, and ozone, which are all considered greenhouse gases, they all responded to which common wavelength? What did they all have in common? Infrared. So how do we define a greenhouse gas? A greenhouse gas then is one that traps or absorbs infrared waves, which what we're going to find out leads to the trapping of heat. Okay, so that's why we say certain gases are greenhouse gases. It also explains that these gases don't just trap heat just randomly. They don't just like absorb heat from the atmosphere, like I absorbed heat. They're literally being shot with infrared waves, and that's the source of the heat. Okay. So, we're gonna watch a really quick video and look at the greenhouse gas effect. And to do that, I'm gonna actually stop screen share so I can pull up this video. Does anyone still need this? No? Okay. I'm gonna pause this and get my video up. Okay, so let's watch this quick video on how green gases work, and then we'll continue on. And as you watch this video, please look for the answers to the questions based on the video. What is preventing us from freezing at night? 2, explain how the motion of air molecules connects to the greenhouse effect. And 3, circle are most or are not most gases greenhouse gases. So you're gonna answer those 3 questions through the video. Okay, so that's your goal as you watch this 3-minute video, to answer those 3 questions.
Moon are basically the same distance from the sun, yet temperatures on the moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder. Thanks so much to the great team.
Okay, do we need to replay that one more time to get the information? No? All right, so go ahead and yes, okay, one more time. You have 3 questions on your notes, so your goal is to answer those, but also it's just interesting. There's a lot more information than just those 3 questions.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
Okay. So, let's go over your questions from the video that you were supposed to answer. Let me get myself back onto screen share. Dun, 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 dun. All right. Show. There you go. Okay. So based on the video, what is preventing us from freezing at night? Our atmosphere. Yeah, our atmosphere traps the heat in. Which honestly is not that surprising. I think the more interesting thing is the whole molecule shaking it idea. But explain how the motion of air molecules connects to the greenhouse effect. The motion and actually the structure of the molecule connects to the greenhouse effect. What do we see? What did the video talk to us about?
Some molecules are electrically lopsided, and so they hold electrons close to one side, so they're able to absorb.
Okay, so electrically lopsided. Another way of putting it is you could kind of think like polar molecules, right? Where you have regions of different electronegativity. That's not an exact equivalent, but you'll find that a lot of those molecules are polar or have polar attributes to them. Electrically lopsided molecules will, what'd you say, Aislinn?
They hold electrons close to one side and are therefore able to absorb radiation.
Okay, will absorb radiation, or another way of putting it is energy, right? Some form of energy. Most of the time they just kind of deflect it, not a big deal. Okay, so as far as though when we look at our atmosphere, are most of the gas particles in our atmosphere greenhouse or not greenhouse? Not greenhouse, because most of the particles in our atmosphere are the very neutral, like nitrogen, oxygen, okay? That make up what, like 70% of our atmospheric particles, okay? So that is a good thing, but is also indicative from the other side of it of how crucial even the small amount of particles is changing our environment, at least what we are observing, okay? So what you're going to do now is there is an article for you to read. I have it printed up here in front if you have to have like a physical copy. And you're going to fill in from your article reading the following two tables. This table on page 3 and this table on page 4. you might be flipping back and forth in your notes because the way the article is working, it's like constructed does not necessarily align with the tables. You're going to see that there is information between the two tables that you find in maybe one paragraph of the article. Okay. And then what you're going to do is you're going to answer these 3 questions. Okay. And we will hopefully go over these 3 questions before the end of class. So I'm going to give you guys about 15 to 20 minutes to read this article, fill in the 2 tables on page 3 and 4, and try to answer the 3 questions on page 4 and 5. All right, guys, good luck. All right, so this article particularly focused on these 4 greenhouse gases. We don't really hit up ozone that much. And so in your reading, we get water, carbon dioxide, methane, that's the common name, nitrous oxide, and yep, those 4. What we see here is we kind of have a really great overview of the source of each greenhouse gas. So we read in our article that water, its main source as a gas is the vapor from the evaporation of basically the ocean. Surface water is like ocean. It's considered a natural, right? 98%. As far as how much of it is in the atmosphere in terms of the gas particles out of, all the gas particles in the universe, how much of it, or sorry, not universe, in our Earth atmosphere, how much of it is contributed to water? And we say 0 to 4%. But it accounts for what percentage of increased greenhouse gas emission? 0%. Okay. So that's kind of why we don't really freak out about water, actually. Despite it being a greenhouse gas, we're not really super concerned about it. Okay. Kind of going down to the second table, we look at water and compared to CO2 as our kind of our benchmark of a greenhouse gas. We say that it technically has higher warming capabilities than carbon dioxide, as it does account for 70% of Earth's greenhouse effect. But here's the thing, the lifetime of that gas molecule is what in the atmosphere? 9 days. So it cycles pretty fast, right? It goes the water cycle, right? The precipitation down to the ocean, down to evaporation, so on and so forth. How many ways can the molecule vibrate with IR light? 3. And as far as is the warming effect currently changing? No, because we're not seeing a drastic change in the water supply. Okay. Okay. So now let's go to carbon dioxide. Carbon dioxide is emitted from combustion reactions like the burning of fossil fuels, like all of our coal power plants, right? Driving vehicles, others, and so forth. Wildfires for California are a big carbon dioxide pump into the atmosphere. Considered 96% natural, and it accounts for about 0.041% of all gas particles in our atmosphere. But particularly, how much does it account for as far as increased greenhouse emission? Holly? 81.3. So despite being a very, very small amount, right? We see that it is responsible for 81.3% of the greenhouse effects that we are studying. And when you go down to the second table, we are comparing CO2 as our benchmark. And we say that 40% is absorbed within how many years? 20 to 200. Okay. So 20 to 200 in 20 to 200 years, 40% of all carbon dioxide molecules in the air are essentially absorbed, which basically means that they're non-worrisome anymore. Like they're not actively present to be acting as a trap, a heat trap. But 60% remain in the atmosphere for over 250,000 years. That means we aren't getting rid of these carbon dioxide. We're not filtering them out. There's no cycle taking 60% of them out of the atmosphere. They're staying in the atmosphere for 250,000 years. Okay, so how many ways can the molecule vibrate with IR light? 4 ways, but only 3 are activated, are considered activated. Now, as far as is the warming effect currently changing, you could kind of say yes if you think about deforestation and the different ways that we're creating mechanisms that output CO2. So it could be like a yes, because of deforestation, as well as the different industrial methods that we are adding to the equation. Okay. So now let's go to methane. Methane is burned as a fossil fuel. It's also a product of transportation and the digestion of cows, animal farts. Cow farts are usually the most significant source. It's why cows stink really bad. And released from buried waste in landfills. China takes a lot of our landfills. Methane's terrible pollution, right? Terrible pollution. Methane, really, really toxic environments, okay? Really toxic regions in China because of how much landfill they have. We say that natural is about 35 to 50%, but most of it's actually man-made. It's mostly due to man-made sources. It makes up even less of the possible greenhouse gases in the atmosphere, but it accounts for how much of the emission in terms of accounts for how much of the effect that we're seeing. 9.5. So when we look at methane, we see that it actually has a higher warming potential than carbon dioxide. Pound for pound, the warming impact of methane is how many times greater than carbon dioxide? 20 times greater. So it's 20 times theoretically more effective at warming our environment. But here's the thing, the average methane molecule remains in the atmosphere for how many years? 8. So it doesn't stay as long. So it's really powerful, but it's got a short time span. Okay. How many ways can it vibrate? 9 ways, but 4 activated. And as far as the warming effect changing, yes, you could say yes, because again, we're creating more human sources that more man-made sources of methane that increases the overall output. Okay. So what about the last one that this article discusses? Nitrous oxide. Nitrous oxide is smog. So when you guys get your car smog checked, your parents do, right? This is why. If you've ever driven to LA or San Francisco, you've seen it. Where I'm from, Denver, Colorado, you can drive coming from like the suburbs of Denver. As you drive into downtown Denver, you can actually see the brown cloud is what we call it, the smog cloud over our entire downtown. Okay. Of course, we don't think about it when we're downtown, but you know, it is a product of many factory processes, but has highly regulated been since the Clean Air Act of 1970. It counts for, again, a really small percentage of all the greenhouse gases, but as far as its effect, what's its percentage on impact? 6.5, but this is actually not what it used to be. That Clean Air Act of 1970 has drastically changed the presence and impact of nitrous oxide in our environment. Emissions have decreased by how much since 1990? Oh, 63.7%. Okay, so that's a great thing, because if you look at nitrous oxide, it is the worst at terms of intensity of warming. Pound for pound, the warming impact of nitrous oxide is how many times greater than carbon dioxide, our benchmark? 300 times greater. If you want to talk about punch, right? A pack for what is that? It packs quite the punch, right? This is it. This is why we see it being actually a really great thing that we see a law regarding it. An average nitrous oxide molecule remains in the atmosphere how many years? 114. So it's not as bad as 60% of carbon, but it sure ain't great. Okay, like it will stay. One single nitrous molecule will outlive you. And if it's got a 300 times greater warming impact than carbon dioxide, it's got a much bigger impact, okay, than statistically comparing your age time. So, or lifespan. So how many ways can the molecule vibrate with IR light? 6, and they all are considered activated. Is the warming effect currently changing? Well, not really, in fact, but it did change. In the past, it changed. It decreased because of the law, but that was a past change. It really hasn't changed that much since. We haven't been doing much with nitrous oxide. So based on the data, What patterns did you notice between how many ways a molecule can vibrate with IR light and the molecule's warming potential?
And
Yes.
the more ways a molecule can vibrate with ions, the more warming potential.
Yep. So the more ways it can vibrate, the more warming potential. Generically speaking. Because if you think about it, that's like saying there's more ways for it to respond to IR and therefore more opportunities for it to trap heat. More heat gets trapped. Okay. Based on the data, what do you think the atmospheric water vapor, why do you think atmospheric water vapor is not as much of a concern as other gases when there's more of it than other gases? Do you want to try, Michaela?
Water remains in the atmosphere for only days while the other greenhouse gases stay into the years.
So water only remains in atmosphere for days at a time. Okay, compared to longer lifespan other gases. I'm going to do GHG, greenhouse gases. In addition, don't forget water is on the lower IR activation spectrum, lower IR vibration. It's only got 3. So it also just doesn't quite have as many ways that can respond. Based on the data, both methane and nitrous oxide cause more warming than carbon dioxide. But why are we more concerned about carbon dioxide? Technically, nitrous oxide and methane are standardly isolated far more dangerous and potent than carbon dioxide. What's the concern with carbon dioxide?
Because we produce so much more of it.
Okay, it's high, it's in mass production, but what else is very concerning?
I
Min?
think it stays in the atmosphere
Mhm.
longer.
It's the lifespan that's really concerning, is the really long. So there's no way that we're cycling out these molecules. So it's the result of mass production, but it's also its crazy lifespan. So what's going to happen is Monday is you will get a progress report little packet where you get a little bit more information, and you're going to use our notes for the past 2 days up until this point in your notes, plus the new information that you get on the packet that you will receive Monday, to write a CER that explains which molecule out of all the greenhouse gases, these 4, not all of them, sorry, these 4 greenhouse gases, is or should be considered the most dangerous and why. And you're going to be asked to use data from the article readings that we summarize in the table. You're going to be asked to connect it to your scientific principles, okay, in terms of trapping infrared and so forth. And you're going to be asked to then write up an article for, I think it's worth 4 points, your CER. You will then submit that Monday, hopefully by the end of class period. And you're welcome to work with people in terms of getting drafts done and modifying, but I don't want you necessarily like handing in the same CER. But you're welcome to help each other, make sure that you have ample amount of evidence and it's a logical flow process. Big thing that you guys need to work on in your CERs is how do you make an argument that makes sense? Not that just has all the elements, but that it's organized in such a way that it's fluid. It's a fluid argument that helps you climb to the peak of your conclusion. Okay. So that's what Monday looks like. That's the end of our notes for today. And the rest of the time is 15 minutes. You can start working on your corrections if you have any. I did submit grades or getting in late work. So go ahead and take that time. Good job, you guys.